Okay, yeah. Okay, so here I'm defining simply the usual Mandelstam invariants you're probably familiar with, right? P1, P4 squared. So you have these three invariants, they're not independent, S hat plus T hat plus U hat is equal to 0. And so, but anyhow, you can still use all three of them. And for instance, you see this amplitude here will have a pole in T hat because of this exchange in the T channel. Other amplitudes have a pole in S hat. Others have more diagram and have combinations of terms and so on. But in essence, computing this, and you can do it yourself to take one of these and try to do the exercise of computing such an amplitude. It's really kind of trivial. And so then you can write, once you have these amplitudes, what you do is you write an expression for your cross-section. And the cross-section at leading order, the Dijkstraff cross-section, let me write it in this form. So this sigma Dijkstraff at leading order has this form. So you sum over all I, J, KL, the incoming and the outgoing. You might have a symmetry factor 1 plus delta KL, meaning if the two outgoing K and L are the same, like two gluons or two identical quarks, you must have a symmetry factor. Then you have a flux factor, let me simply call it F. And then you have here the integral in dx1, dx2, the Pdfs that we mentioned, I, x1, scale mu2. The second PDF for the other particle J, x2 mu squared. Then you have these Platonic cross sections. Let me write it in this form, phi2. This is for I, J going to KL. These are essentially the matrix elements that I wrote before. And then you integrate over the two particle phase space. This is a two body phase space for two outgoing particles. And if you want, you can put, let me write a function, something like theta cuts. For instance, you can impose that your jets are above some given PT. Right? This is in general what you call, if you want, this is a measurement function. You can impose your constraints. This is the usual phase space, and so on, matrix elements, and so on. Right? Now, so we have seen that in the lab frame, you can write this now P3. Let me write it using the parameterization that I used before. You can call it P3, the rapidity, Korsakoff rapidity of Y3, PT cos phi, PT sin phi, and then you have PT, sorry. Okay, and for particle 4, essentially you can write the same thing. So the PTs of these two particles will be the same because of momentum conservation. So let me write it directly using momentum conservation. They are back to back in PT, but they have different rapidities. Y3 and Y4 are different. Now what you can check, again, it's a trivial exercise, is that the rapidities, the PT and the rapidities of the particles are directly related to the variables x1 and x2 by essentially these relations. And x2 pt over square root s. Okay. So how does one show this? Well, in essence, you require that x1, so you impose one is x1, x2 s. So the center of mass energy should be equal to, this is the S hat, this should be equal to P3 plus P4 squared. This is the first relation that you use. And then you need a second one to find x1, x2. The second relation is you use the rapidity of the system. So you use that the rapidity of the center of mass system is 1/2 log of x1, x2. And I don't know if you're familiar with, so then you equate this rapidity to the rapidity of, this has to be equal rapidity of P3 plus P4. And this is, so this is essentially the rapidity of P1 plus P2. This is really easy to show. You write P1 as E x1 0 0 x1 and P2 E x2 0 0 minus x2. So they have momentum fraction x1 x2 and opposite directions. Now if you now compute the rapidity of this system, you see that it's given by that relation. So you can essentially, what this tells you is that the rapidities and the PTs give you information about x1, x2, or so you can you can transform from one to the other. What you can also do then, and maybe this at this point you should be able to see directly, is that the rapidity of say this particle free in the center of mass frame, so objects in the center of mass frame, I put a hat on, this is equal to 1/2 y3 minus y4, right? And this is in the center of mass frame, the two have to be back to back in angle, so this obviously have to be equal to y3 hat squared. Now this relation, if you want, okay, I'll let you think about this. But so what this means then is that, again, you can relate this rapidity, this you know, you can relate to the scattering angle in the center of mass frame. So if you measure the difference between the rapidity of two particles, this gives you direct information on the kinematics in the center of mass frame, even if we cannot really go to the center of mass frame because we don't know the information. So then at the very end, what you can do is, if you want to really compute a cross section, you put this information in a program, right? And essentially, you can then write it in different forms. Let me, for instance, write this schematically. What you can write is that the cross section for digits, differential in rapidity and PT. Let me write a proportion because I'm not sure here about the overall factors and so on. But it has roughly this form where you sum of all particles ij, kl, you have the symmetry factor that we mentioned. And then once you do work out the kinematics, you get this expression written in this form, x1 mu squared of j x2 mu squared, and this differential cross section in the phi2. Now this is an expression that one can take and essentially implement in a computer program. So you can really write a somehow Monte Carlo integrator that generates random numbers x1, x2, picks the PDFs, sums over this, and so on. So I hope I convinced you that computing these cross sections at leading order is really somehow to some extent trivial and easy. And I want to now show you some. So this cross section is exactly what I was writing before. This differential cross section in PT, differential in Y. Differential here means that you took slices of rapidity. So you measure jets that are forward or a bit central or more forward and so on. You see that the more you go forward, the smaller the cross section is. And what you see here are calculations. These, in fact, are calculations at one order higher, next to leading order. But you see this beautiful agreement of data with predictions. Now, we talked about PDFs the other time. So I want to also show you, these are somehow really relatively recent plots. And I want to show you some of the, somebody was asking about uncertainties on PDFs. And this is a sample example where you can see this, right? You see, these are different PDF feeds here, different groups, and one can ask, you can see how well they agree somehow with each other. So how well these curves agree, how well the uncertainties agree, and so on. So this is roughly the state of the art in these calculations here. And now, why are these calculations useful, or what can one do with this? Well, as I said, jets enter everything you do at the LHC, and I will also talk more about jets in general. But for instance, this plot shows you how, by measuring jets at very high PT, your senses, you can constrain new physics. You can constrain models that predict resonances, for instance, like little bumps here. And for this type of, as I already said, for this type of bump hunts, all you need to see is that there is no bump. You don't really care so much about the shape that you control when you do these higher order calculations. But there are also studies where you really improve your sensitivity on new physics. This is one example, for instance, where new physics, for instance, if you have a substructure of, if quarks would have a substructure, the structure of the couplings would be different. So you don't see a resonance, but you see a shape difference because simply because the couplings are different. And here you see an example where you would have substructure, and you will see that the effect of the effect that you have. And of course, here the picture one should have in mind is that the more precisely you can measure, the more accurately you can compute, the more you can constrain even small deviations. And yeah, so I hope I convince you that somehow when we talk about leading order, so what we call leading order is really straightforward and automated. And this was automated a long time ago. Again, schematically, all we have is that we write something, if you want, like this, a matrix element, a measurement function. So this is a phase space, can include PDFs and so on, matrix element, measurement function. This is now very schematically, right? But to compute the matrix elements at a given order, once you know who is incoming, who is outgoing, all you have to do is you draw all Feynman diagrams. You explicitly put in your Feynman rules, get an amplitude, simplify the amplitude, square it, and then integrate over this phase space, flux factor, put in something that is your measurement here, and so on. But everything is really kind of completely straightforward. And in fact, this was automated already long time ago. So people don't do this by hand. I mean, I showed you this example of digits because you immediately start seeing that you start having a lot of sub-processes, a lot of diagrams. So while the calculation is trivial, you don't want to compute so many terms by hand. But this can be very simply automated. Right? So the only bottleneck that you have is that when you go to very large multiplicity, you start getting a lot of terms when you do calculations. So at some point the computer breaks down in this. So as an example, let me tell you exactly. So if we suppose that we compute an amplitude now focusing on jets, we look at, say, gluon going to n gluons. So we want to compute a cross-section with n jets now in the final state. So you can compute how many diagrams you have as a function of n. You can start trying to count. And in the case of two gluons, it's very easy. Now you have the S exchange, U exchange, T exchange, and then you have the 4-point vertex. So these are four diagrams. Then we have 3 gluons, and you have a bit more, 25. 4 gluons, we have 220. 5 gluons, we have 2000. And if we continue, if we go to say 8 gluons, we have something like about 10 million diagrams. So it's clear that, first of all, you cannot do it by hand, but also if you try to use Feynman diagrams, as I told you, you just draw the Feynman diagrams, compute the amplitude and so on, the calculation becomes incredibly slow. Right? So you essentially cannot do this on a computer. So people thought about alternatives to this. And in fact, one of the most powerful alternatives is very, very old and is due to Berenskile. So Ferenczi recursion relations. This really dates back to 88, so it's really very old. But what they said is that you can compute, so they were talking about helicity amplitudes. This essentially means that your gluons have a given helicity. You split them, you know, they have only two helicities, and you can talk about amplitudes with fixed helicity. And they said that you can construct helicity amplitudes recursively using what they call off-shell currents. So let me try to, in a picture, show what this means. So when I put a cross like this, it means that this particle is off-shell. And then here I have an interaction. So this is one gluon, and then here I have many gluons coming out. So this is what I want to compute. And what they said is that you can write it as some linear combination of, write it in this form. And I will explain a little bit what this means. We do it like this. For instance, so we know that in QCD we have only 3 and 4 point gluon interactions. So when I want to somehow reconstruct a full amplitude, or when the only ingredients that I have are 3 and 4 point gluon vertices. So what I said is that you can reconstruct a higher point function by putting together, using this here, 3 point and 4 point gluon vertices, you construct any higher point amplitude in terms of this lower point off-shell currents here. Now, this relation is powerful in essence because the same amplitude, for instance, you see even in this little drawing that I did here, this bit here is exactly the same one as this one, for instance, in this example, right? So you compute these off-shell currents, you store them, and they enter as building blocks of more complicated amplitudes, but you compute them always only once, and they re-enter over and over, right? So this was somehow, this is very powerful, and this is what in fact enters a lot of modern computer codes. There were also other approaches were suggested. Let me just mention them. So for instance, in 2004, Brito, Cachas and Feng suggested something similar. So again, recursion relation, where you construct something recursively. So a higher point function in terms of lower point functions, but using on-shell relations. So somehow here they started, if you want, with an amplitude that involves, let me draw it now, something with 6. And they said this can be written as, again, as a combination, where when I write the sum, it means you have to take all possible combinations. But of these lower point functions, where, however, this, sorry, here I wrote 6, so these things are now on-shell and have a given helicity. So in order to, if you have a 3-point function, in order for all 3 momenta to be on-shell and massless, you have to introduce complex momenta. So they introduce these complex momentum shifts, and they reconstruct amplitudes in this form, where you sum over the minus plus, and you have to sum then over the plus minus and minus plus, so all possible helicities as well. Also, something else was suggested around the same time. Let me write it here. Again, in 2004, this was due to Casciasso and Witten. And here they were talking about MHV amplitudes. MHV means maximal helicity violating amplitudes. So maximal helicity violating amplitudes are interesting because it's well known that they have a very, very simple form. Typically, you can write gluon amplitudes as one single term. And what they were showing is that you can take an amplitude, say with a really generic configuration. Let me write it like this. So these are all external gluons. This is an amplitude. And what they could show, let me now write this form. Maybe let me start putting some. So maximal helicity violating means that you always have two gluons have a opposite helicity compared to all the other ones. So in all the amplitudes that enter here, you always have two minuses and all the others are plus. So somehow, so if you look at this one, this is an MHV amplitude. This is also an MHV amplitude. This is also an MHV amplitude, and so on. So this was also something that was suggested. At the end, because they use more properties that have to do with gluons only, the other two methods, these last two, are not so easy to generalize when you have quarks or when you have massive particles. But these are all valid alternatives to Feynman diagrams. And as I say, at the end, the one that really is used really a lot is this Behrens-Giller recursion relations. Now, so I hope I convinced you that in terms of leading order, we can really do everything, right? Now, leading order has the advantage that compared to our calculation, it's always, if you do a leading order calculation, typically you get very quickly a result. And so it can be also useful in particular if you do beyond standard model physics. If you want to test something, see if there are large effects or not, you would certainly do a leading order calculation. So it's useful if you want to explore new grounds, see if there are big effects or not. But clearly, leading order, you have no precision in a leading order calculation. So for instance, to really say what I mean, suppose that you look at a cross-section, say a W with 4 jets. This is one of the important backgrounds that you have, for instance, for SUSY searches or whatever. It has a missing energy, lepton, jets. Now, if you take such a cross-section, the cross-section starts, because you have 4 jets, the leading order starts at alpha s to the power 4. Now, I told you that we know the coupling to about 1%, but you can change the coupling really by a lot by changing the scale here. And in particular, when the kinematics is complicated, you don't know what is the proper scale to put in the coupling. So if you change the scale in such a way that alpha s changes by, let's say, plus minus 10%, which is very reasonable, you immediately see that your cross-section changes by plus minus 40%, because there's this power 4 here. Okay. So plus minus 40% means that something that is 1 can become 1.4 or can become 0.6, right? So the difference between these two numbers is more than a factor 2. So this is a statement that at leading order, you don't even control the normalization of your result. When you change the scale in the coupling constant, you really completely change the normalization of your result. Also, okay, obviously at leading order, I will tell you more about jets later, but at leading order, we assume that one parton is one jet. There is nothing like substructure. Now we know that, for instance, a lot of tools that look at the structure of jets, and this is completely absent if you do just a pure leading order calculation. So it's clear that you need to go beyond the leading order. And I also want to show you one of the plots. This is one of the oldest plots that I found that really shows that even data really long time ago, this we're talking about 95, the first data from Tevatron, already there, one could see that leading order, so this blue line, is not sufficient to reproduce data. So this is as a function of the center of mass energy. You can look at the Drell-Yan cross-section, WZ, and you see that data clearly indicate that you need to do next to leading order calculations. Okay, so now if you do next to leading order, so as I said, well, if you have and sorry. Okay, cool. I don't know, it will stay. So if you take a cross section that involves n jets at leading order, we said that you do a calculation, you get alpha at some scale to the power n times a coefficient. And this is also what I told you already. The same cross section at leading order, both expressions. So this A is a coefficient that depends on all your kinematics that you have, on your momenta, say, the center of mass, energy, and so on. But at leading order, you're free to change the scale. So these two expressions are really equally valid. But you see that when I take the ratio between these two, this A cancels. And all I'm left is with is the ratio to the coupling to some power n, so this normalization effect. Alternatively, you can also write it in this form. This expression written down here, you can always write it as alpha s to the power n. You change scale, you say, well, this is the same, I can relate it to that. And then I introduce, well, let me do it like this, 1 plus I change scale, so I have n powers of alpha, for beta, beta 0, alpha of mu, log of mu prime over mu squared, plus higher orders. So if you have a leading order cross section, you don't know what scale you should put in these powers of alpha. So this effect is an overall normalization, or one can say, well, I express one scale as a function of the other one, and then I can see that this effect, this one here, is in fact a next to leading order effect, right? Which I don't know, I didn't compute the next to leading order corrections. Now, what happens if you instead do compute the next to leading order correction? Well, if you compute the next to leading order correction to the same quantity, what happens is that you get the following result, sigma n jets at n alone. So the leading order will be the same. You have alpha s to the power scale mu. You have this coefficient, let's call it again this A. Then you get alpha s to the power n plus 1, this is the next correction. You get a coefficient, now let's call it B. And then out of your calculation, you must get a term that has this form. Log of mu squared over something. Let me put q squared. So you must get a term that compensates for the scale variation that you have. So if you change scale here, this will give rise to this orange term, and this you have this compensation mechanism that starts kicking in. This is the first order at which this happens. So again, then the scale dependence will come from the variation of this term here, the green one, and will be an x to leading order effect. The other thing that you see explicitly is that if you do a calculation at next to leading order, you do get these terms explicitly. They must come out of your calculation, this one. So if, this is something I said already, if you choose a scale mu that has nothing to do with the hardness of this process, this q squared, then you will have large logs in your perturbative calculation, and then in essence, you will see that the expansion is not convergent very well. You can get very large corrections. I will show you examples really here. The other thing to say is that, and again, I will show you an example of how this really works, that one can use this scale dependence. The fact that you do a calculation, you truncate the expansion, you get a dependence on the scale, you can use it to estimate the uncertainty on the missing higher order terms. Maybe, okay, I didn't have any breaks so far. Other questions, or should I continue? See many chat messages?
I don't see questions, but I mean, if they want to ask, maybe it's a good time.
Okay. Otherwise, let me continue.
Yeah, there's one.
There's one. Okay.
And Catherine?
Hi, thanks. This is from a little while ago, but the calculation methods you were talking about, I forget the name of it. It was like started with a BG, Bordeaux-Giel, maybe? The one from 88? Yeah. This is maybe sort of an obvious question, but do the final state particles have to be constant in each of the terms in the series?
Sorry, I didn't answer. You're referring to this slide here?
Yes. Does the number of final state particles have to be the same in each term in the series?
Yes. So you see, I mean, the drawing is horrible, but here you see you have 6. So these are 6 gluons, for instance, 6 gluon amplitude. And this momenta, the external ones here and here, this external momenta, they are on shell and they are the same as these ones. Right? Yeah, on shell.
And then for the first method, is the number of final state particles?
So the first method works like this, that again, so how should I say it here? The external particles, so these ones, again, maybe here I didn't even count correctly, but they have to be the same. These match exactly these ones, right? So the external particles are the same in this. So I understand that the picture is not very clear.
No worries, that was my guess. Thank you.
Yeah. However, maybe this orange can help a little bit understand so if you look at this orange, you see that it is exactly the same, it's supposed to be exactly the same drawing, 4 external particles. These are really the same 4. And this block enters both diagrams that I drew here. Right? And this block can be constructed from smaller blocks that again have this form. It's a product of currents that are always put together. So this little block, again, this one here, the one that is in this orange thing, that involves 4, can be written, well, in this case, how can this be written? It can be written as a combination of these blocks, right? You have only one triple gluon. This is a triple gluon vertex, really. These are gluons here. These are all gluons. These lines are all gluons in this picture for now. And then, okay, when you have only 3 objects here, this little block, this, let me change another color now, this yellow block at the very end, this is nothing but the free gluon vertex. Because at this point, this is, you cannot reduce it further, right? So at the end, the idea here is that you start putting together amplitudes, putting together 2 gluons, connecting them, and you call these off-shell currents. And then these building blocks, you compute all the building blocks, but then you reuse them over and over again in the amplitudes. Well, if you compute Feynman diagrams, you essentially, you can have very complicated Feynman diagrams where only one little piece is different, but you recompute over and over the same things. And here you don't do it. You compute everything only once, if you have an efficient algorithm, obviously. And that's why this becomes, you somehow compute the minimal things you're supposed to compute. And this can also be generalized to quarks, massive, massless, even amplitudes with vector bosons. As long as you define, you have to define what are your, how can you put together, what are the building blocks to put together these off-shell currents, and what are the basic vertices that you have. So what is the most basic off-shell current that you can have? For instance, in this case, if you have quarks, the basic block where you would end up to is a 2 quark and a gluon vertex. No, this is an off-shell current with a gluon connected to 2 quarks. Did I answer the question?
Yes, you did. Thank you.
Okay. Any other questions?
I don't see others, so maybe we can go on. And if there are, we stop.
Okay. Okay. So now let's move a little bit too next to leading order. Now, we can't really do too complicated calculations here, but I want to discuss what happens, what changes, or what are the issues with NLO calculations. So, as Ellie said, for instance, if you do die-jet production, this is your leading order diagram. Right? When you do next to leading order, we have somehow schematically now real emissions and let's say virtual correction. So this is real, where you radiate, and this is virtual. This is very schematic. Again, you have to take into account all diagrams and so on. Right? You have to, for gauge invariance. Now, we already mentioned that these two, real and virtual, are divergent. And I already told you that essentially these divergences are regulated during dimensional regularization. This really means that you take an integral that has the form d4L to pi to the 4. So what you do is you can regularize divergences by changing dimension ddl over 2 pi, where this d convention is 4 minus 2 epsilon. And so something that would have a divergence, so something that is dx over x, this x can be, for instance, if you're doing a real radiation, can be the energy over energy, or the angle over angle, or both of them. So, but these integrals, when you change dimension, become dx over x to the power 1 minus epsilon. So you see, this was divergent at x equals 0. This is now not divergent anymore. You can do it, and you see that you find the pulling 1 over epsilon. So divergences are there, soft and collinear. We know we can regularize them, and ultraviolet have to be renormalized. However, the issue when you do calculations is a bit the following. That if you want to consider a cross-section at next to leading order for some, let's say, jet production or N-jets, then you have to integrate schematically over this real, and you integrate it over the phase space of n+1 particles because you have a radiation, and then you have to integrate the virtual correction, but this integrates over the phase space of n particles. And this is what makes this complicated. So this phase space integrals that I here write super schematically, I mean, maybe should I write it in this form, n+1 d phi n. These phase space integrals become immediately very complicated or higher dimensional. So on one side, you know, you have to integrate over x1, x2, and then you have to, for every particle that you have to integrate over 3 variables. Then you have an overall momentum conservation, but you see immediately that here, the dimensionality is very high. So you want to do these integrals numerically, you want to put this stuff on a computer and let the computer do the Monte Carlo integration for you. But you cannot do it because these things, you know how to integrate them in d dimension, and the computer cannot integrate in d dimension. The computer can only throw in variables per each integer dimension. So this, so you have to find a way of removing the divergences before doing your phase space integrals. That is there. Now there are two methods. One is so-called phase space slicing. Let me just say in word what this is. This is not used much at all, so I don't want to discuss it too much. Phase space slicing means that essentially you take this real contribution, and then when you are away from the divergences, you integrate it numerically. Right? When you approach divergences, you essentially replace your full function with some approximation that you know how to integrate analytically. So you say you slice the phase space. Above divergences, you have exact numerical calculation. Below, you do some approximation, then you can have analytic control on that. You can really do this analytically. And of course, you see immediately what is the issue. Where do you put the slicing parameter? Because if it's too large, you will affect your cross section. You approximated your exact result, and you have to check this. If this becomes too small, you might have numerical instabilities. So this is at the end, it was abandoned. Maybe also because at the time people didn't have enough good enough computers. Anyhow, for next to leading order calculations, what people mostly use are so-called subtraction methods. Subtraction methods, and this I want to discuss a little bit here. What is the idea? Subtraction methods. So again, I have to do this a little bit schematically. So let me write now a real radiation cross section in this form. So the cross section, R means real. We are looking at some jets. I write it now as d phi n plus 1. I have my matrix element, which involves n plus 1 particles. This is a 3-level matrix element, so it's as trivial as the leading order calculation. And then typically now I have a jet definition. So a function that, given n particles, tells me if the event has, so for instance, given 3 particles, this could be a 3-jet event or could be a 2-jet event, a jet clustering, for instance. And then I have the virtual correction. So, wait a second, let me also say this object, we know that has this infrared and collinear singularities. And now let me write this schematically in this form. So I have something, x denotes generically the variable that goes to 0 close to singularities. And we know that the singularity has this form. It's a the energy over energy, the angle over angle. Right? And then we have the loop integral, the virtual correction. Now the virtual correction, schematically, the virtual, you know, is always interfered with the Born. So schematically, let me write it in this form. You have a real part of the virtual matrix element interfered with the Born. So you take the real part. And this, we can write it schematically in this form. It has a pole in epsilon. It's not really finite. So now I somehow have these two objects that both are not finite. And I want to find a way to add and subtract something so that I can implement this in the computer. So far the cross section, the sigma jet at NLO, so far I have this problem. I have this dx over x 1 plus epsilon. This is the dimensional regularization that, however, I cannot really implement in a computer program. My jet function, this depends on my P1 PM Momenta. And then I have the virtual correction that schematically I write as V over epsilon. And I have again my jet function here. Okay. And now we use two properties. One is infrared safety of your measurement. So the measurement here is this jet function. And infrared safety means that in the limit where x goes to 0, so let me write it here. I don't want to change slides. So let me maybe write it here in a corner. So IR safety means that in the limit, so limit, where x goes to 0, my function f n plus 1, this jet function that depends on x, must become the n jet function. So in the limit where an emission is infinitely soft, it is as if the emission would not be there. And then we use KNL, Kinoshita-Lee-Nauenberg cancellation. This says that, again, in the limit where x goes to 0, the virtual matrix element has to be equal to the virtual one. This is what we saw, with a minus sign if you want. I think minus here is a bit, depends on how you define it. Now, if you use this, what you can do is that you add and subtract to this expression the following integral, something dx over x1 plus epsilon v f n j. Now what happens? Now you can combine this with minus sign with the real, and this one, this integral with this one. So in essence, your cross section then becomes takes this form. D sigma or sigma NLO jet. I have now the integral from 0 and 1 in dx over x1 plus epsilon. I have my matrix element with my jet function fn plus 1 jet minus v fnj. And then from this bit, when I add and subtract these terms, this minus with this one, you see that the 1 over epsilon really exactly cancels. So you are left with something that is really finite, order 1, let me write it, f j. So again, this term is now the subtracted virtual that is finite. And this one here, this is the real term. And now you see that for epsilon to 0, the bracket goes to 0. So you can essentially drop epsilon because you subtracted the divergences. And now this is something that you can evaluate at epsilon equals 0, and so implement it numerically in a computer code. Right? And so this is a method that is really used in essentially all next to leading order calculations. And there are different ways in which, so here, I mean, what I sketched is really very, very schematic, not with this, this term here somehow. It's supposed to somehow give you the idea that you subtract something, that you subtract whenever there is a divergence. Now, how you implement this or how you realize this can be very, very different. And there are two main methods that I just want to mention. Somehow maybe just. So one is Catani-Seymour approach, and the other is Frizione Kunst-Signer method. What is called now, you might, the so-called FKS method, and this is Amos Catani-Seymour CS method. They both were proposed, you see, a long time ago, and 96, both of them. And the ideas behind the method is different. Here, Catani-Seymour looks at an amplitude and splits it according to who could emit and who could recoil and where are the singularities. While FKS splits more really looking into regions. So FKS at the end you have less terms and is to some extent more efficient when you have higher multiplicity. So the practical realization of these subtraction terms can be very, very different. But what I want to say is that the way to handle these divergences, how we do it, how we subtract them, has been understood since really a long time. And these methods are implemented in a lot of computer codes that are available public, MCFM, MCNLO, PowerHack, and so on. They use these approaches. So, bottom line is that if you want to do a next to leading order calculation, you have in essence for an NLO calculation, you need three things. You need the real diagrams. These are somehow three-level, but involving one extra particle. But this is really like a Born, only one extra particle. So this is has no problems. Then you need to compute virtual diagrams, virtual correction, so the loops. So here you could schematically write it like this, where you have something like this. Virtual, where you have instead schematically, I don't know how to do it like this, virtual. And then you have the subtractions, so that you can make both finite subtraction. So for a long time, it was the case that, okay, tree level is as leading order, so people knew how to do it. Subtraction, as I told you, was understood very well. And so this really, the evaluation of this type of loop diagrams was a bottleneck for a long time. So people, in essence, did one calculation by one. You do this, write all these diagrams, compute all the integrals at one loop, and so on. And here again, a number of things happened about 20 years ago, I would say now, that really then changes picture completely. One has, again, one approach was still due to Brito-Cachasso-Feng, again, BCF, Brito-Cachasso-Feng, in about 2004. And so they started observing that when you have a loop diagram, let me write it schematically like this. And now let's see if I can. So again, these are the external particles here. Right? And this is the loop now. So maybe I should really join it like this. This is a loop diagram. And what they suggested is that you can compute at least the parts of somehow that you can impose quadruple cuts, so generalized unitarity, quadruple cuts like this. Again, they were using this, if you see this amplitude, and if you cut it, a cut means imposing that this particle is on shell. And for this to be possible kinematically, you have to use complex momenta. But for instance, they could extract in the first approximation coefficient of box integrals. So something like this is a box integral because it involves 4 external vertices. They could extract them by somehow doing these multiple cuts on the amplitudes. So this was one of the first breakthroughs. But it didn't allow you first to compute the full result. The second was a really nice neat observation by the so-called OPP method, OPP in 2006. This is Ossola, Pitao, and So the observation was as follows. When you take a one loop amplitude that even involves many, many particles in the final state, at the end, and in essence, because we live in 4 dimensions, the result that you obtain when you do a calculation always has this form. So your amplitude for, even if you have many particles, n particles, can always be written as a sum with some coefficients. Let me write it I1, I2, I3, I4, I, D, I1, I2, I3, I4. So these are essentially box integrals plus some coefficient C again with all the indices D, I1, I2, I3. So triangles. And B, I1, I2, so also here you have I1, I2, I3, 2-point functions. Okay, so these are what we call boxes, triangles, and these are 2-point functions. So when I write this, so if you have many particles, you can always think that this leg here, the one external leg, is the sum of many outgoing momenta, right? So this could be, for instance, P1, this could be P2, this could be P3 plus P4, and this could be P5 plus P6. And you have to consider really all possible combinations that you can have, right? So then you have some on-shell, so this would be, for instance, on-shell, this one would be off-shell, and so on. Now, so the observation is that the observation, and they provided the proof, that this decomposition really always holds. Once you know that this decomposition holds, then you don't need to compute loop integrals. So if you know this, what we call master integrals, these boxes, triangles, and two-point functions, which we do know at one loop, then you can build a system of equations, and you can extract the coefficients directly by evaluating the amplitude at different points. And if you make clever choices, you start evaluating amplitudes where these C's and B's are 0, you start extracting the D coefficients, then you look at this amplitude, subtract the D part, extract the C coefficient. So you build essentially a triangular system, and then you can really extract these coefficients essentially without doing loop integrals. And so these two, and then really a lot of other progress that happened, means that now this calculation of the one loop virtual part in QCD is also something that we consider a completely solved problem. We know how to do it, and these methods can be automated, implemented in computer codes. And yeah, so this is, for instance, one example of a code where you essentially type in the process that you're interested in. For instance, here this process is all focused on Higgs. You can have a Higgs alone, a Higgs with jets. Here you see Higgs with jet here, two jets. This is vector boson fusion, different Higgs production mechanism, or say with vector bosons here, with top quarks and so on. And so you implement the process, and the calculation is all done automatically by the computer. You can get the leading order cross-section and even an next to leading order cross-section out. And this can be done essentially now for all standard model processes that we have. You see a bit what is the edge of complexity that can be reached. So this is about, this tells you, you look at this. So roughly, when you have more than 4 particles in the final state, the calculation in principle can still be done, but it becomes much slower, and you have also issues more of numerical stability and so on. But in essence, if you have enough computing time, this is something we consider completely solved. So what are people that work on NLO do now? Well, for instance, there is a lot of activity in trying to automate NLO corrections also for beyond standard model cases. So not just in QCD, but also in more generic theories. Or you can look, for instance, at what we call loop-induced processes. So for instance, processes that start like that, or even let me do this. This is what we call a loop-induced process, gluon-gluon, top loop Higgs. This starts, the leading order has a loop, so computing this type of processes, or of course computing not only QCD corrections, but also electroweak corrections. But yeah, I mean, I think here there are no, I mean, there are some practical difficulties, but no real, I would say, obstacles. Okay, now I would like to come back to this issue of scale variation and uncertainties and so on. And to do this, now I want to show you an example. Again, this is the R ratio, so going back to plus and minus, because it's kind of simpler. So, when you do a calculation at leading order, next to leading, and also next to next, which I want to discuss next, what you can do is you put in your scale. For instance, if you're doing Z production at lab, you choose as a scale Q the Z mass. And then conventionally now people, this is something that is really done conventionally, conventional range. you vary the scale by a factor 2 up and down. One can ask, well, why not by a factor 10? You know that if you vary this by factor 10, you will generate a large log, a log of 10. So this, you will have larger uncertainties, but somehow they are artificial. This too is, however, conventional, and it comes about because it works relatively well. And by relatively well, I mean that, for instance, if you take the next to leading order and do this factor 2 variation, you see that the next to, the blue, is roughly within this range here. So this is the range where you do the scale variation here, here. And you see that blue is inside this variation of green. So the next to next is within this band. Now the fact that this happens, I think it's really why this procedure has been is being used and has been used a lot. But you see already here one big limitation of this. There are cases where, for instance, at leading order, we know that this R0, we saw R0 at leading order is proportional to 1 plus alpha over pi. So leading order is just 1, or it's just a constant. So there is no scale variation. If you change the scale here, there's nothing to vary. And so you see that in this case, doing scale variation will tell you nothing about the size of the next correction here. And this, in fact, happens. I want to show this. These are kind of older plots, but they really illustrate this effect nicely. For instance, on the left, you see what happens if you do a scale variation on, for instance, now this is TT bar plus jet. At leading order, you have this shape. This follows the running of the coupling, right? Obviously. Next to leading order, you get this, again, kind of typical shape, this flattening out here. You see that if you take, however, a scale that is very different, your NLO will become, will essentially even diverge at some point, right? Both in both directions. So this factor 2 is a conventional range. And you see why this works nicely. At leading order, you have a larger uncertainty. At an NLO, this uncertainty becomes much smaller here. On the right-hand plot, however, shows something that is an asymmetry. Asymmetry is defined as a ratio of cross-sections. For instance, forward minus backward over forward plus backward. And these quantities, again, you can compute at different orders. And now you see also that here you have to be very careful when you do scale variations. You see that the leading order, here there is a little dependence on the scale. The dependence comes from the factorization scale that you have. But this says nothing about the large jump that you can have. So this is something that one has to be really very careful. When you look at the ratios, people like to look at the ratios because you cancel a lot of uncertainties, but it's also much more difficult to estimate the correct uncertainty when you have a ratio. Now here it's another example that I would like to show. This again is, for instance, a cross-section, I would say W, that comes together with three jets. Now, the two plots that you see, left and right, show the same observable. Is the energy or the transverse energy of the second jet. And this is shown at leading order blue and next to leading order black. Now, if you look at the plot to the left, you would say, wow, this is a horrible convergence of the perturbative expansion, very large negative corrections. If you look at the plot to the right, you see really beautiful convergence. No? The leading order and next to leading order are essentially on top of each other. So what's the difference here? The difference is really the choice of scale here. That is different. So on the left, the choice done is the transverse energy of the W. And on the right, the choice done is the sum of PTs of everybody in the event. And now what happens is that essentially the choice on the left is very unfortunate. Why is this unfortunate? Because if you have, if you look at the PT of the second jet, what can happen is that the leading and the second jet are very hard. They recoil against each other. The W is very soft. It's almost at rest. So this AT is a very small scale. If you take a small scale, you have a large coupling. And so a large coupling at leading order means that the leading order prediction becomes very large. And then you have these huge corrections here. On the right-hand side, in fact, you don't see this anymore. So the conclusion here is that, as we know, if you make a bad choice, you will get large logs, and you will get this bad behavior of the perturbative expansion. And, now, this issue about scale choices, you might see, the more complicated the process is, the more you have freedom in choosing, the more options, let's say, you have in choices that are dynamical, depend on the phase space points, and so on. So there is a lot of discussions on how to choose scales and how to use them to really properly assess the uncertainties that you have. But essentially now, to summarize the status of next to leading order calculations. So for a long time, people were doing these calculations by hand, one at a time, and so on. And now everything is automated. And what allowed this automation is really the following points. One, that one is that you can compute leading order efficiently. You know how to compute leading order efficiently automatically. Two, that through this OPP or VCF relations, you know how to go from one loop, how to reduce this to essentially products of tree level. And then the fact that you have subtractions, you know, subtractions are somehow well understood. So, and the fact that you have the basis of master integral. So the integrals at one loop, we all know them. So essentially these 4 points that you can do this, you have subtraction, you have this, really means that you can really do everything. And now I want to contrast this to what is instead the case when you go to next to leading order. But maybe, I don't know if there are questions so far.
Any questions?
I don't see questions.
Okay. So let me show you now, similar to the plot I showed before. Hello and data was saying, well, you need next to leading. Now LHC data is more precise. Next to leading LHC data now tells us that we also need to go beyond NLO. We really need next to leading order. This is one example. This is, for instance, the cross section for WZ as a function of the energy. But you can really look at very, very different examples. And so NLO is not sufficient. We have to go one order beyond. How is this done? Well, if you want to do next to leading order, schematically, again, schematically, you have kind of, let's say, integrals like this, two loop integrals. You have one loop where, however, you have one extra emission here, or you have this kind of, again, tree level, but with two extra emissions. Okay. Now the problem here is that all these bits are divergent, and the singularities, now the way these singularities cancel here is much more complicated. So again, you have the same problem as before. This guy lives on a two-body phase space. This you have to integrate on a three-body, this you have to integrate on a four-body. All of them are divergent. You have to find ways to subtract all these singularities. And so while at next to leading order, it was soon understood how to do it. This at two loop is still one of the big difficulties, how to do this. There are, at the moment, a number of methods have been proposed. They are being used. They have limitations. They are somehow numerically not very efficient in some cases. Then, okay, what else? We don't have things like unitarity. So we are not able to relate something that has two loops to something that is tree level. So the fact that we know how to do tree level doesn't help so much at two loops. Again, there are approaches on using unitarity at two loops, but it's by far non-trivial. And also, we don't even have the basis of master integrals. In some cases, even if you reduce everything to master integrals, then you still have to compute these master integrals and so on. So this means that really next to leading order is really not automated yet. A lot of things happened, but and a lot of progress happened recently. And the progress that has happened so far has to do with understanding how to compute subtractions, developing more methods, and also better understanding on how to compute master integrals. There are, for instance, new approaches where you relate master integrals to using differential equations, essentially. You find them a solution of differential equations. Okay, so I would like now to discuss maybe one process, Drelian.
Can I ask a question, Giulia?
Yeah.
Are there any methods for matching UV and IR singularities at the integrand level? I mean, before integrating and at one loop or two loop. I read something about one loop tree duality matching ER and ER divergences at one loop for virtual contribution and real contribution at one loop level. But I don't know if this is something that has been developed also for multi-loop integrals, at least at some point.
As far as I know, this has not been developed far. Also, to some extent, ultraviolet divergences, to some extent, not really the issue ever here, because ultraviolet divergences.
No, IR, sorry, infrared divergences.
Yeah. No, so maybe I misunderstood the question. No. So what was the question then, sorry?
No, my question is, I think that if we integrate the energy component of one loop integrals, we come to phase space integrals, and we can match at the integrand level infrared and ultraviolet contribution without the need of counter terms, infrared counter terms, or subtraction methods.
Mm-hmm.
Is there something that has been developed also for multi-loop integrals?
So I think there are people working on that, but there are no, so it's work in progress, I would say. It's
Okay.
part of the many approaches on understanding how to deal with these singularities at the multi-loop level in a more efficient way.
Thank you.
Mm-hmm. So maybe what I do now in the following, I just want to show you some results here. I mean, I think I discussed the issues, we cannot really do calculation. I want to show how are some results when you do these calculations, for instance, for Drelian. This was one of the first calculations done with two loops. And so this plot on the left shows you, for instance, if you vary the scale, what happens at leading order, next to leading, next to next thread. So you see very, very clearly this complete reduction of scale uncertainty, right? Again, you see there are also different continuous line or dash dot and so on, where you, sorry, I lost my bar, where you can vary the scales together or not, but you see this beautiful reduction. The plots on the left, on the right, are very old plots, but I want to show you how things were at the time. So people did next to leading order calculation different PDF sets, and you see that, well, the results overlap, there is a larger band. When you go to next, you see this shrinking of the uncertainty band. Now, this shrinking really means that if you have data, you can use this data to very, very nicely constrain PDFs, and this is what was done at the time. Now the same plots are somehow here. This is here it's a Z production. So here we have Z. This is W minus W plus. This is shown in this form because the plot is symmetric, so you don't need to show both parts. The W minus cross section is smaller, but really what this shows you is this beautiful convergence. When you go from NLO to next, you have a kind of larger jump. But then you really have a reduction of uncertainty, small correction, and so on. So it's kind of really beautiful. This plot again shows Drelian over now very different ranges in mass. And again, you see this beautiful agreement. You see, should appreciate how much this cross-section changes when you're here to when you're here. Now, this changes by 10 orders of magnitude. So this agreement is really fantastic, I would say. And since somebody asked about PDFs and so on, this also shows, so this is a very recent plot now where you take, for instance, the ratio of W plus to W minus. As I said, people like a lot to use ratios because you can, you become sensitive to different patterns in this case. You cancel all the final state QCD part and you become sensitive to initial state, the fact that W plus and W minus are initiated by different patterns. And so you see now how different these are somehow modern fits of PDFs, modern sets. These are plots that, of course, I took from this paper of an NPDF3 because they have, you see, this beautiful agreement. Others agree less well, but it really depends on what you look at. So this on the right, for instance, you see the ratio of predicted over measurements. And you see somehow in some cases, the agreement is not so nice, but this is about the level of agreement that we have in this, something very, very basic, which is Travian production. Right, you see, we're talking about some percent in these uncertainties. Now, the other process that was computed very early on was Higgs production. Now, Higgs, as I told you, really, Higgs, the main production mechanism is this one, where you have a top loop. But people computed instead this in an effective theory, where you shrink this to an effective interaction. And in this framework, you can then compute the two loop corrections to that. And this is what is shown here. And so at the time, people didn't know the Higgs, the mass of the Higgs boson. So plots, you could find many plots where the size of the correction is plotted as a function of the Higgs mass. What is remarkable is maybe on the right-hand side, the result that you get. So what is shown here is what is called the K factor. The K factor is typically, for instance, cross-section at next to leading order over the cross-section at leading order. So it gives you the size of the correction that you have, or the cross-section at next to next, and so on. Now, what is remarkable is you see that when you do a next to leading order correction, you go from 1 to essentially 2 here. So the next to leading order effect, that should be something like 10%. In the case of Higgs production, is really incredibly large. It's a factor 100%. This on one side means that if you want to have precision, you really need also the next to next. And that's why this was computed very soon. But you also see that in this case, as different from Delian, even when you have the next to leading order correction, the uncertainty band that you have is really remains relatively large. So blue and red overlap, but the red band is not completely inside the blue band. There is still a kind of large jump and so on. So in this case, even if you have next to leading order corrections, you still have relatively large uncertainties. Maybe we should have a break now. I see it's past 3 o'clock. I don't know if there are other questions.
Yeah, there is a question. Well, let me. I think Einar could ask directly the question, I think.
Yeah, sure. Hi. I was just wondering why the cross section in a plot that you showed before for production of W minus is smaller than the one for W plus. I mean, I would expect that there should be particle-antiparticle symmetry.
Okay, so let's think about it. So the W plus, if you do a leading order calculation, the diagram that you have is this one. Okay, this is W plus. Now the question is, who are these quarks that are incoming here? You have an incoming quark. So in essence, to produce a W plus, here you must have, you can have, for instance, an up quark. While if you want to produce a W minus, here you have a down quark. right, for simply charge conservation. So it's really related to the fact that in the proton you have more up quarks than down quarks.
Right. Okay. So for instance, if one did E plus E minus collisions, then one would not see such an asymmetry, right?
Yes, you would have to have E alpha, you produce a W with something else, so you would have to do electron neutrino to produce a W, and then
Yeah, right.
PP bar at Tevatron is a better example.
Yeah, right. Yes.
It's a better example, yes.
Because in E plus E minus you cannot do the W. So
Exactly, you would have to have
PP bar is symmetric.
PP
So
bar
it's just a charge.
Yeah, right. Yes.
Mhm. Indeed.
Cross-section is symmetric, yes.
Mhm.
So maybe, Giulia, we can have a break now
Yeah.
and come back at 3:30.
Okay, good. As always, I'm a bit slower than I wanted to be, but okay.
Very good. So I have to close the session though, because of the recordings, and then I will open it again.
You will not. You told me somebody else will, but.
Well, yeah, I open it and then I leave to someone else the sharing.
Okay. Thank you
Thank
then.
you.
Bye.
Bye.
See you later.